Welcome to Breadboarding. In this, the 8th in the series on the NanoComp 6809, we're going to be building the keypad which is necessary to control the NanoComp. Now this we need to produce on stripboard or VeraBoard because the key switches won't easily plug into a breadboard in an appropriate layout. What we're going to look at first of all is our schematic diagram. And you can see here that in the previous video where we added the LED display and keyboard decoder, we added the Darlington drivers, the pull-up resistors and the LED display. So these have all been crossed off now. And what we're going to be looking at now is just the keypad. And what you can see from the overview diagram is the keypad is driven off the Q0, Q1, Q2, Q3 lines off of the decoder here. So that means when the PIA is giving values of 0, 1, 2 or 3 to port B, then it will be scanning the keyboard. And when we're reading the keyboard, what actually happens is the port A of the PIA is set to be input, and by default these inputs are pulled to high, to 5 volts. So by default they'll show high 5 volts, and what happens when a key switch is pushed is only when one of these lines is brought to ground or selected, so it's at 0 volts. When the key switch is pressed, what will happen is that particular PA line will go to 0. So in fact, when a key is pressed, you don't see it as a 1 on the port, you see it as a 0. And again, when we look at the source code from the monitor, we'll see that when values are coming back from here, we're complementing or inverting the values. So just be aware here that when a key is pressed, we get a 0 on the port. So what I'm going to do now is to switch back to the presentation, and we're just going to go into a little bit more of the detail of the keyboard layout. It's quite complicated and very easy to make mistakes. So you can see here with the, I've got the leftover of the key layout here, and we can see that this matrix here in the original design has the PA0 to PA6 lines coming in here. PA6 is not actually used by the keyboard at all. It was only used for controlling the 7-sync displays. So in fact the keypad only needs PA0 to PA5, and then you can see these lines, the Q0 to 3 are coming in here. So when we're looking at the PI signals we need, the keypad doesn't need PA6, but keypad does need the reset and the non-maskable interrupt. And what we're going to look at is what keys those are used for. So this is just a blown up version of the schematic, and all I've done is produced slightly easier to read versions of these to when we want to check things to see which keys are on the various rows and columns. So I think generally call the Qs will be the rows, and the PA 0 to 5 will be the columns. We can also see the reset switch and the abort switch. Reset goes to the reset line and abort goes to the non-maskable interrupt line. That allows us to always stop a running program even if we no longer have control of it. Now here is a diagram that I've consolidated from an Excel sheet I've done. This first one here shows the physical layout of the keypad. So we have 16 hexadecimal digits first. So we've got your 0 to 9 and then A, B, C, D, E, F. So that's a standard hexadecimal keypad. And then these other keys are for the functions of the monitor. So the load and save keys will be used in the future for loading programs over the serial port that we'll add in later versions. This was originally in the 6809 NanoComp, was used for loading and saving memory to cassette tape, but we won't bother with the cassette tape this time around. It's probably easier to write directly to serial port. So load and save will be used at a later point for saving to serial port. We could test these out and see what happens when we look at the PIA lines that were used for the cassette interface, just to see that it's working. Continue button is used to continue from, if we've pressed abort, then continue will continue execution where it was interrupted. Go is used to start a program. So we type go, then type in the hexadecimal starting address, and then it will start. Reset is the hardware reset line. Abort is the non-maskable interrupt, and we'll go back to the monitor and will allow us to inspect registers. Memory allows us to inspect and change memory. Normally you type in the M, then type in the address, and then we press the increment button to go between each memory location. If we want to change it, we type in 2 digits and then press increment. Register allows us to display the registers after we've interrupted our program. We can also use software interrupt codes to do this, and by pressing the I key we'll toggle through the various registers. So this is the physical layout, and the colours is largely based on what colour keys we'll be using. So most of these will in fact be black, and then I think we've got some green and red ones. These other views are interpretations of how we need to look at the key layout from the point of view of physically implementing it. So this one here is a kind of a logical view, just showing a matrix for all of the Q0 rows and all the PA columns, so just so we can look up which one is which. And you'll see there are some gaps. Obviously there's nothing for PA6, and there are the odd gaps here and there, so PA4Q3 doesn't have any code key mapped to it. These other ones on the other side may look a little confusing, but what they're in fact showing is the reverse keypad layout. So when we're going to be building this on a strip board, we're actually going to be wiring things on the reverse side of the board rather than the front side. So the keys are going to go on the front side, but when we look at the keypad from the reverse, then we'll find that reset, abort, memory, register, increment will in fact be on this side. And what this view helps to show is where all the various keys are wired up. So when we look here, the Q0 color, yellow, shows all those keys that share the Q0 line. Similarly for Q1, which is white, we can see all these keys share the Q1 line, and you can see this P4 is just an odd one stuck on the end. When we come to Q0, when we come to Q2, we can see that again we've got these keys sharing the same column, but then the 1 value is then also tagged on the end. And finally the Q3 values show keys that actually share that row, and we can see then the reset and abort, these are wired up specifically to the reset and interrupt lines. They're not part of the key matrix itself. And then this lower grid is still looking from the underside, but this is just showing which keys share the same columns. When we look at PA1, that's the next row down. The only slight confusion is that PA4 is used for these 3 keys here, but then all the other rows are largely all using their associated PA numbers. But you will notice that they don't go in any real sequence. We've got PA5 at the top, then PA3, then PA1, then PA0, and then PA2. So they don't really make logical sense, and I suspect this is more an artifact of the way how the printed circuit board was done in the original Nanocomp back in 1981. What I'm going to show you now is the keypad as I've represented in Fitzing, and in particular the most useful thing about Fitzing here is that we can click on particular Q0 and PA combinations and see which keys are highlighted when those tracks are shown on Fitzing. So let me just switch over to Fitzing. So this is the layout, and again what I've done here with Fitzing, we've got Fitzing rather than breadboard mode, we're doing it in strip board mode, and it allows you to say how many rows and columns you want for your strip board. And you can also see it's quite difficult to see. This is one of the main feedback things I would provide, is that it'd be really nice to be able to provide a slightly clearer identification of where there are breaks on the circuit board. So if we go in some of these, we can see here that there are breaks between some of these lines, but they are quite difficult to see. Another nice thing that you can do here is we can choose to optionally hide various layers. So if we hide the parts, we can actually see the way how the various wires and all the breaks are. So you can see that some of these lines have multiple breaks along them, others are continuous. So what I'm going to do with the layout that we've got here is I'm going to print it out, one with the keys on the layout, the other without, and what I'm then going to do is to go and highlight where the breaks are. But when we look at this, what we can do, if we zoom back out to this in window, so what you can see here is if I click on Q0, I can see for Q0 which tracks and which connections are hooked up. And if I just do some, just move this to the side and we'll find our, so this is the layout I was showing you, and what this is showing you is for a given color which things are joined together. What this allows us to do is, if we look at this, just zoom out slightly. What we can do is when we click on Q0, we can see that those yellow wires that we've got match up with what we can see on the diagram there. When I click on Q1, we can see all the white ones are connected, which again ties up with the top block in our Excel sheet there. Look at Q2, and we can see there all the red ones going down, and then there's also the key 1 straggler on the end there. And then finally we can look at Q3, we can see then all the blue wires there match up. And this is useful to be able to make sure if you've got any stray connections, or some of the tracks sometimes occasionally can get joined if you're not careful. This is the biggest issue I have with fritzing, is that when you're inspecting the layout like this, you can quite often end up with stray wires being put in here. So I'd like to be able to turn off putting in wires by default when interacting with the UI, but it's a very useful program otherwise. Then we're going to look at the reset. This is much simpler. We've only really got the reset is connected to the ground and then to the reset line. I've put 2 lots of connectors on here. I've built an earlier version of this, and what I found is it would be useful to be able to have connectors on either side depending on where you want to put the keypad. So all I've done here is made sure that whenever we're looking at one of these lines, it's also hooked up to the corresponding connector on the other line. We can use either side, just making things a little bit more flexible if we want to use it in further projects. If we look at the non-maskable interrupt, again, we can see there that non-maskable interrupt basically ties the ground to, also uses the ground. So when we look at the ground signal, we can see the ground goes to one side of both the reset switch and the abort switch. And finally, if we look at the PA0 to PA5, so if you look in the lower section of the spreadsheet here, we look at PA0, we're expecting this to be this grey row here. So if I click on PA0, and we can see there that the keys with the yellow highlighting there are on the second row up from the bottom, are F65, but not 4, as the case may be. Then we look at PA1, we're expecting that to be the orange, and that is the 3rd row from the top. And again, those are all correct, and the final key 7 is not highlighted. And we look at PA2, we're expecting PA2 to be the blue row, which is the bottom row of 4 keys, and that's correct. And again, you can see I've drawn these tables accidentally as doing this. And now we're going to look at PA3. So PA3 is the 2nd row down in highlighted in red. Again, that's correct. PA4, we're expecting that to be the 3 white ones at the end. This one is a little more unusual, but we can see there that those keys, the 7, 4 and 1, are all connected. And finally, we'll just test the PA5, and we can see the PA5 is the yellow, which is the top 4 keys. So the way how the 0 to 5 is mapped to these things is not especially straightforward, and I've found that doing this just makes it less likely that I'm going to make mistakes. I'm not promising not to make any mistakes, but it should be less likely with this. So What we're going to do now, I'm just going to print these out. I'm going to print one out with the keys highlighted, and when we turn off the parts layer, you can see that I've got labels for all the keys anyway, and all this matches up with the diagrams here. And we can see when we look on the left hand side, if you look at the physical diagram, then you can see that obviously this is reversed compared to what we're looking at here. So what we're going to do now is to have a look at the components that we're going to be using for this. Trying to find the right key switches is quite difficult. There are a lot of computer PC key switches. Cherry key switches require holes in the printed circuit board to mount them, not only for the pins, but also they have bits of moulding that requires holes in the circuit board. So if we're getting printed circuit boards built, then the Cherry key switches would be fine. But the ones I've got here, I've got from RS Components in the UK. I'm sure there's other places to get similar ones. Certainly if anyone knows of better switches than this, please let me know. I'll be interested to know if there are better options for building keypads than the ones we've got here. So let's have a look at what components we're using. First of all, I've got strip board, a bit of strip board. Now this bit of strip board I think was about 3.5 inches by 6 inches. I think it's 35 holes by 60 something when it started. I've cut this down based on the number of holes required in fritzing. I think it's about 50. I've made the holes in 50. I've also made some mounting holes there, and if we use these type of PCB standoffs, quite useful for mounting it on various breadboard bases and things like that, like the chopping board I showed in some of the earlier videos. So if we use that with these, it means that we've got a way of mounting the keypad. Then have got 25 key switches. They are printed circuit board mounting ones. Thick operation. The only thing we do have to be careful of, and we'll check this, is it's not immediately obvious which of the contacts are connected together. So we'll verify that before we start putting everything together, just to make sure. I believe it is when it's plugged in this way that the top contact and the bottom contact are not connected. So this side and this side are connected, that side and that side connected. And when we press the button here, then the top and the bottom get connected. But we will just verify that, because if we put them in the wrong way around, it will be a big job to try and undo them. So we've got 25 of those. The only other thing I've mentioned before, these are slightly too wide to go into a breadboard comfortably, which is why the reset switch had a little riser for it. They're also slightly too big to go into this strip board. I did paint the strip board. I had some black matte paint, so I've painted the top side of the strip board just to make it look a little bit neater. We can't easily push these in. They will go if you really push, but they become really difficult to come out. So we may just use a printed circuit board drill just to widen some of those holes to put those in, just to make it a little bit easier to pop in and out. The problem being that if we find out that we've put things in the wrong place, it could be quite difficult to take them out otherwise. So in addition to the key switches, we've also got a number of keycaps. So most of them I've got are black. I do have some red and green ones. I suspect I don't have quite enough green ones for the way how I was planning to do things, so I'll either try and order some of those, or we'll just use black for the moment. I have got some transfer sticking labels for doing the key cap labels. That is remarkably difficult to find transfers for doing that. I thought it'd be quite easy, but it wasn't. Then we've got 2 edge connectors. So these are right angled edge connectors, and this is what we'll use for using the various ribbon cables to hook up to the main Nanocomp board. And then I've also done some labels for those so that I'm less likely to make mistakes when wiring things up with the labels on the reverse side of the board. So that's most of the things we've got. I've also got the very useful device for doing these printed circuit boards. This is a PCB sort of stand that I'll be using for doing this. This allows you to hold the PCB firmly and swap sides. So that's quite a useful thing to do. So that's these are the components we're going to be using. And what I'll probably do is to record this, but without audio, and then we'll just speed it up so you can get a feel for what's involved in doing this, but you don't have to spend the next hour and a half, 2 hours hearing me struggling with soldering irons and everything else. So I've got my continuity test here connected to the top pin and the bottom pin. When we press that, then we get a contact. If I remove this and put it on the top pin, then so the horizontal pins are connected together, and the gap between the horizontal pins is where the connection is made. So when we look at the printed out versions of the fitting diagram, you can see that in fact the connections for the wires here are butted right up. One of the things to note is that the tracks between these two need to be broken in the middle of the track between the, there's no spare hole between the two buttons to get the layout right. So what I'm going to do is to solder everything in and then do the track breaks afterwards. And what I found in the past is it's useful to use a PCB drill with a very fine drill bit on. Is easier to actually cut the tracks when you're trying to do things very, very finely. And it also allows you to cut through solder bridges and things like that. If the solder is a little bit too much, you can use that to cut through the solder bridges. So I'm not going to do the cuts in the tracks yet. And also here is the other diagram that I printed out. This is the one without the parts. And you can see here that I've gone through, hopefully, caught all of the cuts in the strip board. It's a lot easier for us to go through all in one go. And now we're going to go through this at 30 times speed. So I'm just going to commentate over the steps here. So what we're doing first of all is marking out where the individual key switches are going to be, making sure the right thing. Then we're drilling out the holes so that they fit in a little bit better. This is your printed circuit board drill, plugging all the switches. Some of them are a little tighter than others. We're going to solder them as we go. So now we're going to put on the labels, and have also stuck in the edge connectors there. And as we go in and cut the wires and tick them off, and then we'll solder them as we go. The soldering iron I'm using has got a very fine tip. Now, for some of this work, this does mean it takes a little while to heat up, but it does have the benefit of not overheating things. So if I was doing this again, I might use a slightly larger soldering iron tip. This speed, it works absolutely fine. So you can see as we're going through, we're soldering these on the underside of the board, and that sometimes means we have to cut the leads to be quite short so that they run into the underside of the key switch. You can see that the way I've done this is tried to make the colours match up the same with the diagram and also with the key diagram that I showed in the presentation. And then you also see we're just going to do the other little red wire for the straggler key switch over on the right hand side here. Now there is a mistake coming up in a few seconds. See whether or not you can catch it. We will be coming back to it a little bit later on. But when I started to test this, I did find there was one problem, and see if you can actually see where it occurs. And the right angle connector fell out, and I put it back in. Unfortunately, I put it back in the wrong place, so I had to desolder it and resolder it. Again, one of the problems with soldering things rather than using breadboards is makes things a little bit more challenging to fix. Okay, so we're just about coming to the end now. So I think this in total was about 3 hours. So you've watched about 3 hours of time elapsed into about 3 or 4 minutes. And then all we're doing is marking where the cuts are that we need to make, and then using the PCV drill to break the circuit and to make sure we break the solder joints where there are solder joints. Okay, and that's just about done. So 3 hours done in not very much time, and just trimming the leftover wires and using the Sharpie pen. Right, so we've now completed the soldering on this. I have done the basic test. I have checked the continuity meter to make sure all the brakes and things were good. So none of those are giving any continuity unless, of course, we press down on the button. So this is the layout as we had it from the underside of the board. So reset on this side, load on this side, and 10321. So I0321. So we're going to turn it over now, and now we're going to plug in the key tops. So if we have a look at so you can see here, we're going to have load, save, continue, go, reset, abort, memory, register, increment, then A, B, C, D, E, F down to 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. So I don't think I've quite got enough green keys at the moment, so I'm just going to use black keys for those where I don't. Perhaps I'm just going to put the green keys for go, for continue, and for increment, I think, for the moment. And then once we've done that, we'll do green for go, green for continue, and green increment, and then all the other ones we're just going to make those black for now. I've tried various sources for getting sticky labels for the key tops, and I'll show you the best solution I've found so far. Not an ideal solution, but it's the best I've found. There used to be keyboards or keys that could come apart, and you could print sheets and put them between the two layers of the keycaps. They had a clear cover. The original Nanocomp keyboard I had those, although I've subsequently lost the keycaps. But there don't seem to be keys like that anymore. And that would allow you just to print out your own sheet and put paper key values between the clear top and the underlying key. So we just need a few more black ones. And we should be good to go. 6 more. Right. Now our keys. So now I'm going to do is to get the stickers to put on here. So here are some of the various keyboard stickers I've got. These are some that I've used on an earlier version, which were replacement key stickers for a standard keyboard. The only issue with these is that all of the symbols were in the top left side of the keyboard, and when I needed numbers and things, then they had all these other things. So it didn't work brilliantly well because I ended up having to cut out these. The first one I had was just a paper-based sticker sheet, and whilst these were okay, but they did tend to get dirty. They weren't great. And I managed to find these ones on Amazon. They are vinyl stickers. They should be about the right size for these particular keys, and although they're not the ideal character set, they are seem to be the right sort of size. So we're going to stick all these on, and then we'll turn the audio back on. Right, I'm just going to do some basic tests here. So I've got a continuity tester here. I'm just going to make sure that we expect the connectors at the edge here to be connected to each other. So you would expect the Q0 to Q0, PA0 should be connected. So I'm just going to go through these connectors and make sure they're all connected. And obviously if we also find other ones which are accidentally connected, then we'll also check that as well. So just going to test that's expected. Then we're going to, it's okay. Let's do the next one up. So expect that one, and let's just, aha, PA1 and PA5. That's expected. It's okay. Do number 4. That's expected. Yep. 5. That's what I'm going to do, is to swap out one of these leads for a crocodile clip. It'll probably be easier. We expect. Let's make sure I don't touch any more pins. We expect. Right, next one. So this one was causing the trouble on the other side. So let's just connect it to that pin. So 0, 1, 2, 3, 4, 5, 6. That's non-maskable interrupt seems to be causing a problem there. It's expected. That's not quite right either. So there's reset. So there's some problems with reset as well. So let's try from the top here. Okay, that's okay. We'll try there. Expected. It's expected. Right, so the issues we seem to have is this pin 5 here, reset. Not attached to reset on this side. NMI and reset might be the wrong way around. Reset to NMI. That is in 0, 1, 2, I'll call it 0, 1, 2, 3, 4. That's going to 0, 1, 2, 3, 4, 5, 6. Starting at 0, 0. 2 NMI. PA1 connected to I. I suspect something's gone wrong with our wiring here. Right, so I'm going to stop the video now. So we've got a few little wiring issues here. So I'm just going to have a look at that, and then I'll come back and explain what was going on, and we'll fix. Okay, so I think I've got to the bottom of the problem. If I just zoom in here, you'll be able to see. So you remember there was PA1 and non-maskable interrupt seem to be connected together. So PA1's down here and non-maskable interrupt is here. And in fact, there were two blobs of solder here, and they were very, very close to each other, probably touching. So all I've done is I've used my drill bit to make a gap between the two. And then the other thing is that we seem to have non-maskable interrupt and reset were connected. And what I realised is when I was checking this, I didn't check it as thoroughly as I should do, even though I was ticking things off. So here we've got one going up to the top rail, another one going to the second rail down, but and over here, second rail, top rail, but in fact, I've mistakenly put in this one is going to the top rail, not the second rail. So I'm just going to desolder this, and we'll move it to the correct rail, and hopefully we should all be. I just might take a couple of shots of the solder sucker. I should be able to lift this out now. Which is one of the reasons why I don't like soldering things. Breadboard, it's much easier to sort your problems out. The only trouble is very fine tip soldering iron. It's great for making sure you don't wreck anything, but it does take a little while to heat things up. Right, so I'm just going to cheat here. I'm just going to make this a little bit more arched and stick this back down in that hole there. We can just lay it flat once we're done. So we'll just get the solder on here, and then hopefully we'll do our test again and all will be well. Solder flow around the copper. There we go. And we'll just make sure that we aren't... It's a good clearance on the track there. And all I'll do is I'll just lay this down a little bit so it's not quite as... Right. So hopefully that should now mean when we test with our continuity meter. So what we had before is when we tested reset, which is the fifth one down here. And there, ground, non-maskable interrupt, non-maskable interrupt. And then the other one was that pin 2 here should go to pin 2. But it was also connecting to non-maskable interrupt. There we go. So looks like we've solved that particular issue there, but it's always worthwhile doing some sanity checks. And what I'm going to do now, in fact, is I'm going to hook this up to one of my test rigs, and we're just going to check to see that when we press the keys that we see the expected signals coming through. Right, so I've hooked this up now. I'll show you the breadboard. And what we're going to do is go through this little matrix here. So what we're going to do is to put in a continuity tester on each of the Q0, Q1, Q2, Q3 lines, and then we're going to check for PA0 to PA5. When we press the key, we're just going to wait to see if we get a beep. If we get a beep, it's working okay. If we don't get a beep, then it's not working. We're not going to bother to test other combinations because I think we've already checked that the wires are now, the pins are not accidentally making contact with other signals that they shouldn't do, because we've already checked that in the previous test we're doing. So I'm going to be looking at this table as I'm doing this. What I've done here is I've just hooked up a Ridman cable, and this is plugged into the breadboard. I've written down on here which signals are which. So over here we've got Q0, Q1, Q2, Q3, and over here we've got A0, A1, 2, 3, 4, 5. So what I'm going to do is I've got my continuity tester here. Goes beep when there's a connection. But all I'm going to do is first of all plug in the continuity tester to Q0, and then we're going to be in brown, which is PA0. Now I'm looking at this this chart whilst we're doing this. We'd expect that Q0, PA0 should be 5. So I'm just going to press 5. Yep, that works. So now if we look at PA1, that should be 8. PA2 should be 2. PA3 should be A. PA4 should be 7. PA5 should be L. Yep, that's good. So we go back to PA0, and now we'll move on to Q1. So Q1 PA0 should be 6. Yep. PA1 should be 9. PA2 should be 3. PA3 should be B. PA4 should be 4. And PA5 should be save, or was punch on the original design. Okay, so that's all good. Now we're going to go to Q2. And for Q2, PA0 should be F. Next one should be E. Then 0. Then C. Then 1. Then continue. And that's all of that one. So we'll go back to PA0 again. And now the final one, we're going to Q3. And Q3 PA0 should be R. Then M. Then I. Then D. Yep. Then PA4 should not have anything, so press all those, there's nothing for PA4. Then PA5 should be G. And then finally, we're just going to look at the ground is the grey. So we're going to hook up ground to grey. And then I'm going to plug this into non-maskable interrupt. So that is the abort key. So we'd expect the abort key to do this, and the reset shouldn't. Obviously, when we did this before, when we had the wrong wires connected, then they were connected together. And now if we plug into reset, we now would not expect abort to work, but reset. So looks like the keypad's all wired up, and it's wired up according to what we're expecting here. So all we've got to do now, we've completed this. So the next video, what I'll be doing, we'll be hooking this up to the peripheral interface adapter and the rest of the NanoComp. We'll be switching it on and see if we can get the monitor to come up on the LED display and use the keypad.